Brady Sperier. I'm the lead for Group 2, and I'll be talking about the Sperier-Group experiment, which is experiment 1. So here's a little bit of an introduction of what I'll be speaking about. I'll go over the relevance of this experiment, some theoretical or thermodynamic background of it, a little bit of a description of the experiment, some required equations and calculations, as well as predictions, and then some potential questions you might have. First, we'll start with the relevance of the experiment. The goals of this experiment are to determine the latent heat of vaporization of water, and to do this for varying pressures and temperatures, and then to compare it to tabulated values. So practical applications for this would be in fields of meteorology or any other kind of aeronautical or research organizations such as NASA and any other organizations of that nature. Some theoretical or thermodynamic background. We have this Sperier-Group equation, which describes the latent heat vaporization of water, as you can see here. And then below it you have just the various parameters within the equation itself. This is one way to put the equation. There's another way to write it, where you use ideal gas approximations, and more notably this third term here is the only thing that's changed from the previous equation. A description of the experiment, we'll start with the apparatus. We have 10 basic components, more notably a big 1,000 milliliter flask, a hot plate, thermocouple, pressure transducers and gauges, as well as valves, water reservoir, pump, and a data acquisition system. Here's a depiction of the apparatus. Just your basic components. You have the data acquisition, the hot plate and flask, and then the pump, reservoir, and feed valve. With any experiment, there's always uncertainties. With this experiment, more notably, you have the type K thermocouple with some statistics or some values for range, accuracy, sensitivity, and then the general use of a type K thermocouple is kind of an all-purpose or general purpose thermocouple. Procedure: 4 basic steps. You're going to first set up or configure the data acquisition system to make sure it's ready to record data. Second, you're going to check and verify your equipment, verify its integrity, and see that it's safe to use. Third, you're actually going to conduct the experiment by putting water in the 1,000 milliliter flask, putting a vacuum on that flask, putting it on a hot plate, and then recording the pressures and temperatures along the way. Once the hot plate's turned off, we're going to cool everything down and shut everything down and clean up to make sure it's ready to go for the next experiment. Some equations and calculations that were stated in the lab manual. He wanted us to provide a pressure versus temperature plot for saturated water vapor, as you'll see on the next slide. Along with that, we want to calculate the latent heat based on these 4 parameters, which I've done here below. I started with the basic Sperier-Group equation using the ideal gas approximation, and then further solve for latent heat here at the bottom. And we want to take these values that we find experimentally and compare them to tabulated values for latent heat. Here are pressure versus temperature plots for water vapor that I found on the internet. As you can see on the left-hand side, you have English units, and on the right-hand side, you have metric units. Some predictions for this experiment, for the experimental results. I predict that the results will fall within plus or minus 15% of tabulated values, and I think this will happen because 2 possible sources of error, one being the experimenters or the operators. That's a large uncertainty there. And then secondly, the equipment. Equipment, as far as I'm concerned, might be used. It might not be in the best shape. And then some questions you've probably been dying to ask, but I'll probably get to them before you have a chance to. First, you might ask how the location of the thermocouple might influence the results. Well, that's actually very important because the positioning of the tip of the thermocouple will largely affect the temperature reading. For example, if you have the thermocouple all the way at the bottom of the flask with contact at the bottom of the flask. It'll be closer to the hot plate and will then give you a higher temperature reading and won't give you a true reading of the liquid inside. So it needs to be, I think what the lab manual said, it needs to be at least 3/4 of an inch off the bottom of the flask. Another question you might ask yourself is, how does a vacuum pump operate? That's a very good question. A vacuum pump operates by what you might think by vacuuming air or other fluids from any kind of confined space that you need to put a vacuum on. More notably, you use a vacuum pump to remove air from a confined space or control volume. Okay, and there's another question, but I don't think we have time to get to it. But in conclusion, this is what we talked about today. Here's my sources, and are there any questions?
Yes, go back to your